We are going to discuss a relatively small topic in this video, which is called thermal strain and deformation. So that's thermal strain and deformation. With the changes in temperatures, the solid bodies, most solid bodies will change their dimensions. If the temperature increases, generally the body expands, and if the temperature decreases, we could say the solid body will contract. In normal cases, or in most cases, over a limited range of temperature change, this expansion or contraction is linearly related to the temperature change. So now you can see a similarity between the Hooke's law and thermal strain and deformation. In Hooke's law, we say over a certain range, stress and strain are linearly related, which is the same concept here. Over a certain range of temperature changes, the strain is linearly related with the temperature change. I'm just mentioning Hooke's law so that you can link both of them and study the concept or understand the concept of thermal strain easily. So if for a homogeneous isotropic material or for a homogeneous isotropic body, the thermal strain by, say, a temperature change of delta T can be expressed as the thermal strain epsilon, let's call epsilon T, is directly proportional to the change in temperature. And we know the proportionality can be changed into an equality, and we write it as the thermal strain, which is epsilon due to temperature, is equal to alpha delta T, where alpha is the coefficient of thermal expansion, just like Young's modulus in Hooke's law. In Hooke's law, we had stress directly proportional to strain, and we changed the proportionality to equality by using a constant called Young's modulus. Now, alpha is the coefficient of thermal expansion, and because strain do not have any units, you can see the alpha should have a unit of per degree, or 1 per Kelvin, or degree Celsius, or whatever the temperature unit here. Usually in because it's a delta T, you do not have a unit, but we say this is per Kelvin. The unit of alpha, or coefficient of thermal expansion, is per Kelvin. Now, this is the property of the material, coefficient of linear thermal expansion. If you to be precise, it is coefficient of linear thermal expansion. That is a property of the material. Usually equal thermal strains develop in every direction of an unconstrained body. For example, if you have a body which is sitting on a frictionless plane, then the thermal expansion will be same in all direction, just like this. However, if you have a body which is constrained at any plane, then thermal expansion will be limited to the planes or the surfaces that are free to expand. Usually you will have an expansion as the temperature increases and a contraction as the temperature decreases. Now, the extensional deformation due to a change in delta T or a change in a temperature can be or the deformation can be calculated as say this is thermal deformation is equal to alpha delta T. Note that this is change in temperature and this is deformation, that's why the suffix T here, and this is not T, not as a suffix because that is the change in temperature, times if you are calculating the deformation in length, then this will be L0, because you know the strain is change in dimension over original dimension, which is L0. So change in dimension is what we mentioned here. So that is change in dimension due to temperature, that is a thermal strain. And if you will also have a change in due to thermal or temperature with the initial diameter or initial width or whatever unit you are considering, and using this equation you can find the change in dimension on the or the change in dimension on the particular cross section you are looking at. So if you are looking at the change in length, then this will be applicable. Alpha delta T times L0 will give you the change in or increase or decrease in length with the change in temperature. This equation is quite often used in calculations, so it is absolutely necessary that you understand this concept for doing problems that involves both the thermal and stress force stresses. Wherever you have a thermal stress, you need to apply different forms of this equation to find the change in dimension and the required forces or required supports that will be required, that will be needed to prevent or contain those changes. So the change in length or change in dimension is alpha delta T times the original dimension. In here we are talking L0, but it can be a radius or a diameter or whatever dimension that you are considering. So once again, thanks for watching. Keep watching the videos and look forward for more videos. Thank you.